closer and closer, just 2 steps to go. We've now shown that phi r is a bijection. We've shown that it preserves addition. We just have to show that it preserves multiplication. And we'll be done showing that phi r is an isomorphism and that in fact then there is an isomorphism from x to y. Then the last step will be to show that in fact this is the only there's only one isomorphism between x and y, and we will be completely done with our exploration of the construction of the real numbers. And then we'll be moving on to multivariable calculus. So we've been doing a lot of good work in the last few videos proving the addition and the bijection. And I think we should have the techniques we need under our belt by now. So if you've watched the previous video, you should be able to anticipate where we're going. If not, then make sure you've watched those previous videos. And if you have any questions, of course, ask me in the comments. So to start with, multiplication, of course, is at the same time more involved than addition because multiplication of positive reals is almost identical to addition of all reals. So the first part of the proof is going to be almost identical to what we just did. But the problem is that because multiplication deals with negative numbers in such a convoluted way, there's a lot more involved in order to get to finish this step than there was with addition. So without further ado, the first step is to prove multiplication for positive reals, and then we'll extend that to all the reals. So, okay, so we want to prove that phi r of u times v. And throughout this, I'm going to use the times symbol just because I think it's a little, it makes it more similar to addition than otherwise. Equals, it just highlights the similarity. To u, phi r of u times phi r of v. This is what we need to prove. First, we're going to prove it for when u and v are both elements of the positive reals. So the first thing to note is that since phi r is order preserving, then phi r of 0 in x equals 0 in y, then phi r of u is greater than 0, y, and phi r v is greater than 0, y. So the first step, we have that if u and v are positive, then phi u and phi v are also going to be positive. With multiplication, it's kind of odd because they're not both multiplicands. It's actually one's a multiplicand and one's a multiplier, but that seems like a completely arbitrary distinction to me. I don't know why they don't just call them both multiplicands. Anyway, okay, so special case. U is an element of x plus, v is an element of the positive rationals. So the set d of u times v is the set of all r element of q where r is less than u times v. So the one difficulty in this, if you remember when we were proving multiplication of Dedekind cuts, the one difficulty about multiplication is we're dealing with positive Dedekind cuts, but the Dedekind cut is a set of all of the rationals to the left of the number. That includes the negative numbers. So even though these numbers are going to be positive, the set of everything to the left of these numbers will include negative numbers. So we're going to have to be careful about that at a certain point. And for now, I think it's not yet an issue. But keep an eye on this. I think I've caught every place where it matters, but maybe I miss one, in which case let me know and we can correct it. So r is less than u times v, and then also note that means you can divide both sides by v, and you have that r over v is less than u. Okay, make a new variable q equals r divided by v. So observe that r and v are both rational numbers, so q is a rational number. And because r divided by v is less than u, q is less than u. And r equals q times v is less than u times v. Next page. So the set phi q of d u times v is the set of all phi q of r, where r is an element of the rationals and r is less than u times v. So, since q is multiplicative, we also have that phi q of r equals phi q of q times phi q of v. Because we said on the last page that r equals q times v. So since phi q of du times v is the set of all phi q of r, it's also the set of all phi q of q times phi q of v, where q is less than u. So the set of all phi q of q times phi q of v, where q is less than u, is again the set of phi q du times v. Now note, remember that phi q of du is by definition the set of all phi q of q, where q is less than u. That's just the definition of phi q of du. So again here, we can rewrite this so that phi q of q equals phi q of r over phi q of v. So that means that since phi q of du is the set of all phi q, it's also the set of all phi q of r over phi q of v. Since phi q of du times v is the set of all phi q of r, which equals phi q of q times phi q of v with q less than u, then since this is the set of also of all phi q of q with q less than u, we can use this to rewrite phi q of q as phi q of r over phi q of v. So we can then say that the set of phi q of du is the set of all phi q of r over phi q of v. Okay, with this in mind, we want to show that phi r of u times v equals phi r of u times phi r of v. So if we rewrite these, the definition of phi r of u times v is the supremum of the set of phi q of du times v equals the definition of this is the supremum of phi q of du. And again, using P3, since v is rational, phi r of v equals phi q of v. Okay, so with what we've done so far, we have rewritten the problem in terms of phi q. We have now some information about this set and this set, which should allow us to prove this statement, which then gives us that. Next page. So we have that phi r of r has to be less than the supremum of phi q of du times v. That implies. So now we can just divide through both sides by a number. And so we'll divide through by phi q of v on both sides. And that means then just rewrite this, and we have that phi q of q is less than sup phi q du times v over phi q of v. Okay, so the set of all phi q with q less than u is the set phi q du. That's by definition. So if phi q is less than this, and this is everything in here, that means that this is bigger than everything in phi q of du. That means that this is an upper bound of phi q du, right? So that means that we can say then that the supremum of phi q of du is less than or equal to this whole thing, the supremum of phi q du times v over phi q v. So again, we're almost there. This is phi r of u, this is phi r of v. So if you multiply both sides, you have phi r u, phi r v is less than or equal to phi r of du times v. The problem is the less than sign. So assume that this is less than this. Then what do we do when we have an inequality? We insert a rational number between them because they're dense. So then there exists a t element of qx such that sup of phi q du is less than phi t is less than sup q du times v divided by phi q of v. So if phi q of t is less than this, and this is all phi q where q is less than u, all rationals less than u, then t has to be one of those rationals. So phi q of q equals phi q of t. In other words, the t is one of those. That means that phi q of t is an element of phi q of du. Therefore, phi q of t is less than or equal to the supremum of phi q of du. And we've reached a contradiction because we started by saying that phi q of t is bigger than the supremum. We concluded that phi q of t is less than or equal to the supremum. That's a contradiction. So the assumption must be wrong. And we have what we wanted to show, which I'll put on the next page. We've shown that this is not less than, so therefore this has to be equal to. So we've shown that supremum of phi q of du equals the supremum of phi q of du times v over phi q of v. Now, this is the definition of phi r of u times v. This is the definition of phi r of u. Phi q of v equals phi r of v. And I multiplied both sides to move this over. And that's what we wanted to show. Okay, so we've shown that phi r preserves multiplication when one of the multiplicands is rational. So far, that proof was exactly like it was to prove the addition. So now the general case, let u and v be elements of x positive, and let q be an element of the positive rationals in x, such that q is less than v. Okay, now v is any real number, but q is a rational less than v. Now, this is where it matters that we're only talking about positive numbers, because the Dedekind cut is everything less than v, but q is only positive. So the set of all q less than v is not actually the set of all rationals less than v, because we still have to add the negative rationals and 0. So we'll take care of that, but that's the one little awkward place in this part of the proof. So q is less than v. That implies we can multiply u by both sides, that u times q is less than u times v. That implies, now phi r is order preserving, so that implies that phi r u times q is less than phi r u times v. So we just showed that phi r preserves multiplication when one of the multiplicands is rational and both of the numbers are positive. So this step is still okay. So we can rewrite this now because we just showed that this equals u times phi r of q, that's what we just showed, is less than phi r of u times v. Then we can just divide both sides by u, and we have that phi r of q is less than phi r of u times v over phi r of u. And finally, since q is rational, we can change that to phi q of q is less than phi r of u times v over phi r of u. Okay, now we're going to have to start dealing with Dedekind cuts. So let's go to a new page. And we're going to have to define something a little different here. So let P be an element of all the rationals such that P is less than V. So note that the set of Q is an element of the positives such that Q is less than V. So the set of all Q's less than V is a subset of the set of all of the rationals less than V. So that means then that the set of all phi Q of Q is a subset of the set of all phi Q of P, right? Because these are only positive and this is all of them. So we basically just extended our positive all the way to include the negative. So now we can talk about Dedekind cuts. So with this in hand, the set of all phi Q of P with P less than V is the set of phi Q of D V. We couldn't do this with Q because the set of all phi Q of Q is not this full set, but with P, with all of the negatives as well, then we can. So if phi Q of Q is less than phi R of U times V divided by phi R of U, then if this is true for all Q less than V, then phi Q of P is less than the same thing. Right? Because this is a bigger set of everything less than Q or less than V. And since this, the set of all phi q of p with p less than v is the set phi q of dv. That means if this is larger than everything, then this is an upper bound of phi q of dv. So phi r u times v over phi r u is an upper bound of phi q dv. And if this is an upper bound, so the supremum phi q of dv is less than or equal to phi r of u times v over phi r of u. So now, again, we're almost there because this is the definition of phi r of v. So we have that phi r of v is less than or equal to phi r of u times v over phi r of u. So we have to assume the opposite. Start on the next page. Assume phi r of v is less than phi r of u times v over phi r of u. So there must exist a t element of the rationals such that phi r of v is less than phi q of t is less than phi r of u times v over phi r of u. Now phi r is, oh wait, I said q, but this should be r. I can rewrite this as r because t is rational, so they're the same. So phi r is order preserving. So if phi r of v is less than phi r of t, that implies that v is less than t. And notice that since v is positive, then t is also positive because it's bigger. Okay, so then we have that phi r of t is less than phi r of u times v over phi r of u. That was given. That's less than phi r of u times t over phi r of u. That's because v is less than t, so this has to be less than this because phi r is order preserving. And since t is rational, we know that phi r preserves multiplication, so this is the same as phi r of u times phi r of t all over phi r of u. Cancel these, and what do we have? Therefore, phi r of t is less than phi r of t. That's impossible. That's a contradiction. So we assumed this, reached an impossibility. That means that our assumption must be wrong, and therefore phi r of u times v equals phi r of u times phi r of v, right? Because I just multiplied u by both sides when u and v are elements of the positive reals. Okay, good. So now we've reached the point that we were with addition. We've shown that phi r of u times v equals phi r of u times phi r of v when they're positive. Now we have to extend this to the negative numbers, and then we'll be done. So there's going to be a few steps to this yet again. The first thing we have to do is show that phi r is preserves multiplication when one factor is 0 or plus or minus 1. Once we have this, we'll be able to decompose the problem, and it'll all fall out from there. So this is actually pretty straightforward. So for positive 1, phi r of 1 equals phi q of 1 equals 1, because we established a long time ago that 1 goes to 1. So therefore, we have that phi r of x times 1 equals phi r of x equals phi r x times 1 in y equals phi r of x times phi r of 1, right? Because we just showed this, so 1 equals phi r of 1. So we just showed that phi r of x times 1 equals phi r of x times phi r of 1. That's 1. Now 0. So first note that phi r of 0x, same thing, equals phi q of 0x equals 0y. With this, we can do almost the same thing. We have that phi r of x times 0 equals phi r of 0. That equals 0 in y. That equals phi r of x times 0 in y. And that equals phi r in x times phi r of 0. Phi r of x times 0 equals phi r of x times phi r of 0. That's that. And now finally negative 1. So what we need to show is that phi r of minus a equals minus phi r of a. So let b equal minus a. Since phi r is additive, we have that 0y equals phi r of 0 in x equals phi r of a plus b, right? Because b is minus a, so a minus a is 0. And this equals phi r of a plus phi r of b, because phi r is additive. So what we just showed is that phi r of a plus phi r of b equals 0. That means that this must be the additive inverse of phi r a, which is minus phi r a. So we just showed that b equals phi r of minus a, and it has to equal the inverse of phi r a, which is minus phi r a. So that's what we wanted to show. Okay, so it follows then that the same is true if the number is 1. So then we have that phi r of minus 1 equals minus phi r of 1 equals minus 1 in y. Okay, so phi r of minus 1 times a equals phi r of minus a equals minus phi r of a equals minus 1 in y times phi r of a equals phi r of minus 1 in x times phi r of a. So what did we do? We started with minus 1 times a, and then minus 1 times a is minus a. That's the same as minus phi r of a. That's the same as minus 1 times phi r of a. And then minus 1 is the same as phi r x. And then, so this equals phi r of minus 1 times phi r of a. So we started with phi r of minus 1 times a, and we ended up with phi r of minus 1 times phi r of a. Okay, so we've shown that phi r preserves multiplication if one of the factors is plus 1, 0, or minus 1. Now with that, we're going to be able to go through and show that then with this being true, it's true of all real numbers. So arbitrary. Okay, so let's define two little things. Let the absolute value of a be a if a is greater than 0, and minus a if a is less than 0. Okay, and let sigma a, the sign of a, equal plus 1 if a is greater than 0, and minus 1 if a is less than 0. Okay, so let u and v be arbitrary elements of x. Then we have the phi r of u times v. This is actually quite simple. You might want to pause the video and see if you can do this yourself. Using these two things and what we've just shown, can you split this up into phi r of u times phi r of v? So the first thing is to split both of these up. So this equals phi r of sigma u times the absolute value of u times sigma v times the absolute value of v, right? That's not doing anything because u is an arbitrary, so it's just the sign of the number times the absolute value of the number, same there. Now, this is just four numbers multiplied together, so we can rearrange them because they're commutative. So that means that we have phi r of sigma u times sigma v times the absolute value of u times the absolute value of v. Now you should be able to figure out what we're going to do from here. So we can split this up because we showed that whether this number is either minus 1 or positive 1. So that means that if we put parentheses around these and around these, we can split these up because we know that phi r preserves multiplication for minus and positive 1. So we have that this equals phi r of sigma u times phi r of sigma v times, these are both positive numbers, and we know that multiplication is preserved for positive numbers. So it's times phi r of the absolute value of u times phi r of the absolute value of v. Now, go backwards. Rearrange them. We have that phi r of sigma u times phi r of the absolute value of u times phi r of sigma v times phi r the absolute value of v. Now, this is a positive or minus 1. That means that phi r preserves this multiplication, and same here. So now we can rewrite this. We can group these. Phi r of sigma u times absolute value of u times phi r of sigma v times absolute value of v, right? Finally, sigma u times absolute value of u is u, so we have phi r of u, same with v, times phi r of v. That's it. Therefore, phi r of u times v equals phi r of u times phi r of v. QED. Okay, we are done. We've shown that phi r preserves multiplication. And we've already shown that it preserves addition and that it's a bijection and that it preserves order. That means that phi r is an isomorphism. And now we've shown that there is an isomorphism from x to y. So we've shown that there's an isomorphism between any two ordered fields with the least upper bound property. It's interesting how from the beginning, when you're dealing with addition and subtraction and even fractions, it's all pretty simple. But once you get into the least upper bound property and real numbers, it vastly complicates the entire picture. And now when we're moving on to multivariable calculus, of course, calculus is all about limits. All the time that we talk about Dedekind cuts and how, it's every rational number, there's always a bigger rational number, even though they're always less than a certain barrier. That's what calculus and real analysis is all about. Is that the epsilon delta notation, that no matter how small it is, you can always find one in between. That's what real numbers are, and it's very complicated, very difficult to get from rational numbers to this bigger set that includes this least upper bound property that eliminates the gaps. And of course, we've already talked about this, but the amazing thing is that rational numbers already, there's no largest rational number in a bounded set either, but even so, there are still gaps, and that's what this least upper bound property allows us to fill in. So now we're showing that, in fact, there's only one of these sets, which is very interesting, because usually, as we talked about a long time ago with groups, there are multiple isomorphic different kinds of groups. There are not multiple ordered fields with the least upper bound property. There's only one. So there's something special about these real numbers that once you've defined them, you've filled in the gaps, they're complete, and that eliminates a lot of the room for rearranging them. And that, I have a feeling, is very much a part of why we're talking about this at all, because this kind of rigidity then limits your choices in other areas as well. We have to make connections, and that's where we have to go. So we have one step left to do, which is to prove that, in fact, there's only one isomorphism from x to y. If you think that you can come up with two isomorphisms, we're going to show that those are actually the same isomorphism. With that, we'll be done with our construction of real numbers entirely, and we'll move on to multivariable calculus. Thank you. See you next week. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.